Okay, let's continue. Now some steady flow devices. Okay, now this is a gas turbine, okay, where electricity is generated. They are simple devices. Now here what you see is air enters from here, okay, and let me see. Here we have the compressor. So air is compressed. It is called a low pressure compressor. And then more stages of compression. Each stage is, compresses the air more and more. So air is compressed to high pressures, like 10-20 atmosphere. And then we have fuel right here, okay? It is sprayed into the high pressure, high temperature air. So we have a combustion here. So fuel is burned. So the temperature rises. And then it goes through the turbine right here. These are turbines, high pressure, low pressure. It forces the turbine to rotate and work is generated here. Then it is connected. So we have the power output. Here we have the energy input. So the energy of the fuel, chemical energy in. Okay. And then here we have the hot gases. There leaving. So this is what we do on land. In the case of jet engines, they are a little different. Okay. Okay, this is the land-based, what you see here, a little more color here. You can see the blades, okay, for the compressor. I will show you later on the case of jet engines there. Okay, now let's analyze the nozzles and diffusers. Okay. Now this is the case of jet engine. In the case of jet engine, we have at the inlet very high velocities of air because the planes are going like 1,000 kilometers per hour. Okay, so in that case, you need to slow it down to increase pressure. So here we have a diffuser. And then this is the compressor, okay, schematically, as you see here. And then the burner or combustor right here, okay? And we generate a little work to run the equipment, so a small turbine here. And this part is the nozzle, as you see, okay? The area gets smaller. So here you have, high velocity gases leaving and producing the thrust. In the land gas turbines, you don't want that. But if you are on an airplane, this is what you want, together with the work generated there. So this is the nozzle, and right here, and this is the diffuser. The diffuser slows down the fluid, raises the pressure, and nozzle accelerates the fluid, okay, and drops the pressure as it does it. So converts the pressure to velocity, nozzle, whereas the diffuser at the inlet converts the velocity to pressure. So we will analyze these, but this is what they do. So schematically, a nozzle increases the velocity and a diffuser decreases the velocity. And here the pressure goes up, and here the pressure goes down during this process. Okay. So how do we analyze this? First of all, you notice that these are one inlet, one exit devices. One inlet, one exit. So they are single stream. Therefore, we don't need the summation signs. And this operates, okay? The amount of mass at any given time inside is constant. So is the amount of energy. at any given time. Okay, therefore, mass in equals mass out, mass flow rate, and since at 1 and 2 they are the same, we just use m dot with no subscript. Okay, and for energy entering is equal to energy leaving. So how this is how we analyze nozzles and diffusers. Now, in general, the change in velocity is very significant. So we keep the kinetic energy term, as you see here, and of course we keep the enthalpies because they represent the intrinsic energy of the fluid. But usually the heat transfer is very low, so this is usually neglected. So if a problem makes no mention of heat transfer, okay, you can just assume it is zero, because it's typically small compared to other energy terms. And we never involve work, so this is always the case. There is no shaft or other things crossing, or electrical wires crossing to nozzles and diffusers. So work is always zero. And these are usually small devices, so elevation change is small. So you can say that the change in potential energy is always zero. Then, maybe with the exception of heat, this may be significant sometimes, the energy equation takes this form, meaning the enthalpy and kinetic energy terms, their sum remain constant. Okay. Okay, this is an actual picture. Now this is the a jet engine. You see the nozzle. Okay, the cross-section area is decreasing. It is getting small here. At the beginning, the cross-section area is increasing. So this is the diffuser, and this is the nozzle here. And in between, you have the compressor, combustion chamber, and some turbine there. Okay, now let's show it with an example. I think this is a picture that I took myself. This is the diffuser of a jet engine. Okay, and this is the airplane. You can see the wheels there. Okay, now air at 10 degrees C and 80 kilopascal, high elevation, obviously. At sea level, it will be about 100. Enters a diffuser of a jet engine steadily with a velocity of 200 meters per second. Okay, so this is probably like airplanes taking off, still at low altitude. They usually reach like above 200, between 200 and 300 kilometers per hour before they can take off, depending on the weight of the plane there. But in meter per second, this is that. And the inlet area over the diffuser is this one, 0.4 square meter. The air leaves the diffuser with a velocity that is small compared to the inlet velocity. It means velocity 2 is much smaller than velocity 1, which means kinetic energy 2 can be neglected, okay? But 1 is a large velocity, cannot. The turbine, the mass flow rate of air, m dot, the temperature of air leaving the diffuser, so P2, okay? So assumptions, we assume steady flow process, okay? And we can assume air is an ideal gas. We can always assume that, unless the pressure is like, you know, megapascals, several megapascals, like 10, 20, 100. Okay. And potential energy change, we can assume it is zero. There is no mention of elevation anyway. There is no mention of heat transfer, so we can assume heat transfer is negligible. And we can assume kinetic energy at the exit is negligible. And there are no work interactions, which is always the case there. Okay. So energy balance in the rate form, energy minus energy out, energy change, okay, in the rate form. steady, so this is 0, as you see here. So energy entering must be equal to energy leaving per unit time. Okay. And in this case, at the inlet, the mechanisms are the energy of the mass, which is enthalpy, kinetic energy, which is this, potential energy, which is neglected, and then enthalpy at the exit, kinetic energy at the exit, potential energy, which is neglected, work, there is no work, and there is no heat. So energy equation becomes this. Cancel the mass flow rates, they are the same. You end up with for H2 is H1 minus the change in kinetic energy. Of course, this also will be 0 there. Okay, this is how we do the energy analysis, energy balance. Okay, it's an ideal gas. So I can determine the initial specific volume. Okay, then or I can also calculate density, doesn't matter. Then the mass flow rate is 1 over specific volume, or density times velocity times cross-sectional area. These are given. Okay, so here is the mass flow rate. The energy balance we just did reduces to this. This one is 0. This one is given. H1 is H at 15 degrees C, which is 283 Kelvin. So from air table, we read this one. Okay, and this is the value we read. So plug in the values, you get 303. So the exit temperature is 303. Initial temperature was 283. That means we have a delta T of about 20 degrees. Okay. So as you see, as the air enters, the entrance temperature is 283, okay, which is 10 degrees. Okay. The velocity decreases, the pressure increases, we can show that also, and the temperature increases. Okay, now question. Initially we had kinetic energy at the beginning, and at the end we don't have any kinetic energy. What happened to the kinetic energy? Anybody? Yes. It is converted to enthalpy. Right?
Oh, sorry.
Right? So enthalpy has increased from 283 to 303.14. So the energy is still there. So we get this, okay, based on conservation of energy. So if you look at the energy forms, I mean, this equation says that the energy forms involved are enthalpy and kinetic energy. Okay. And kinetic energy goes to 0, decreases. Then conservation of energy says enthalpy must increase by the same amount. So this is conservation of energy. So energy is accounted for, and what we are doing here is an accounting of energy. Okay, let's do another one. This one using a nozzle. Okay, steam nozzle, really. They are used a lot in steam turbines. Okay, we have steam at 1.8 megapascal, 400 degrees, and the entrance area cross-sectional is 0.02 square meters. Okay, and the mass flow rate is 5 kilogram per second. It is steady operation, so it remains constant. Okay, and steam leaves the turbine at 1.4 megapascal, so the pressure drops, and the velocity is 275 meter per second. Okay. And there is also some heat loss, 2.8 kilojoules per kilogram of steam. Question is, what is the inlet velocity and what is the exit temperature? Okay. So what is the velocity here? And what is the temperature here? So question clear, right? It is a nozzle. Okay, obviously, I can determine the velocity here from conservation of mass, okay? Because mass flow rate is density, which is 1 over specific volume, times cross-sectional area, times velocity, okay? I know the mass flow rate, okay? And I know the cross-sectional area, and I know the state at the inlet. So if I can determine V1 and A1, I know M1 anyway. This is the only unknown. I can determine V1, the velocity one. So initial state, 1.8 megapascal, 400 degree. I go to steam table, okay, which is the superheated vapor. This is table A6. And I read V1, specific volume, and H1, okay, from this table. And at the inlet conditions, M is 1 over V1, velocity 1, cross-section area 1. This is given. I just read this one. Area is given. So velocity 1, I can just solve for it. And this is what we get, 42.1 meter per second. Okay, energy balance, steady operation. Okay, therefore, the change in energy is 0, as you see here, which means energy in is equal to energy out. Okay. And no mention of potential energy. We have heat, so we will keep the heat transfer there, but no work. So energy in 3 mechanisms. What? The energy of the mass, heat, and work. Work is not there. And heat at the inlet, entering we don't, but at the exit we have heat leaving. And mass, the energy of the mass, enthalpy, kinetic potential, there is no potential. So this is energy of the mass, and at the inlet, this is energy of the mass at the exit, and this is the heat leaving. If you divide by mass flow rate, the whole equation, you will get H2 is equal to H1 minus Q out minus the change in kinetic energy. So this is the simplified form of the energy equation. So conservation of energy requires this. So this is how you can calculate the enthalpy at the end. Obviously, it depends on how much heat is lost, okay? And of course, the initial enthalpy, and also the change in kinetic energy, because that change also should appear in the final energy, enthalpy there. Okay, so this is the relation. Okay, H1 we just read from the table. Okay, and Q out is given. Then velocities, V2 given, V1 calculated. Okay, this is the conversion factor that we include. See, everything here is in kilojoules per kilogram, right? The enthalpies. But this is meter per second squared, and this will give you normally joule per kilogram, right? To make sure that this term is also in kilojoule per kilogram, we use this conversion. 1 kilojoule per kilogram is 1000 square meter per second square. That means you divide the result that you get from here by 1000, and you get this. So at the end, if you know two properties, you can determine any other property. It is a state postulate. This is the final pressure and this is the final enthalpy. You go to the superheated vapor table again, find this pressure, and underneath, see, it is like, you know, temperature for a given pressure. P is 1.4 megapascal. And then you have specific volume, you have enthalpy, whatever. Once you find the enthalpy value here, H2, you simply read the corresponding temperature, which is T2. So in this case, it is 378.6. Okay, and the temperature here drops by 21 degrees, 21.4 degrees. So the enthalpy is going down. Okay, what happened to this energy? Enthalpy is decreasing. Okay. Why did enthalpy decrease?
Because
okay,
we are losing temperature.
Okay, no, we don't use temperature. We are losing heat.
Sorry, I'm sorry.
Okay, there is a heat loss and there is a change in kinetic energy there. So the whole thing, you know, balances out this way. That is the change in enthalpy, the change in kinetic energy with the correct signs, and the lost heat. They should balance each other. Okay. So here, as you see, we have enthalpy dropping. Heat is lost. There is some heat loss there, but not much. Okay. But the drop in enthalpy is mostly balanced by the increase in kinetic energy. The velocity goes from 42 to 275 meters per second. Okay, any question on this example?
Can I
no
ask
question.
a question?
Yes.
A question ago, we find increasing temperature. But here we are losing temperature.
Yes.
Usually, if any energy turns to heat, we say it's a efficiency problem. Am I right?
Yeah.
But second question, we lose heat.
Yeah.
What will we say for efficiency on that?
Okay, now anytime you lose heat, it is bad. That is, see this 2.8 kilojoule per kilogram. Okay, this is lost. Okay, so you don't want to do that. That is because it went to the atmosphere. It became here. Let's say you could maybe use part of that energy inside. Okay. Here we have nozzle, and the goal is to make the exit velocity here maximum. And if you lose energy, it will not be maximum. Here the velocity is, okay, let's look at the values, 275, right, meter per second. And at the inlet, let's say 42 meters per second. Okay, so the reason we have a nozzle is to increase velocity at the expense of the energy of the steam. Okay, and it increased from 42 to 275. So this is the desired thing. Okay, this is what we want. But could this be maybe 280, 290 possible? Okay, what is the efficiency of this? Now, normally what comes to mind is, okay, we can use the increasing kinetic energy divided by the change in enthalpy. That will be the efficiency. It will be roughly correct, but not exactly. Okay, We don't define the efficiency that way. What we do is, assuming the process is perfect, that is, there is no heat loss and also there is no friction here, then the ideal velocity we would get, and we would compare the highest possible velocity, okay, to the actual exit velocity. And we will do this in chapter 7, okay? So you will see how the efficiency of the nozzles are defined there. But basically it is related to the actual exit kinetic energy divided by the maximum possible under the given conditions kinetic energy at the exit. Okay. Other questions? Okay, then let's continue to other devices. This time turbines and compressors. Now turbines, again, you can see the blades here. Okay, the compressors are also very similar, but they work in reverse. So when you have turbines and compressors, obviously the work term is most important, the shaft work. Turbines generate shaft work at the expense of the energy of the fluid. So the enthalpy will go way down. And compressors, they consume shaft work. So the energy of the fluid will go up. Also keep in mind that when we say compressor, we mean work consuming devices. So compressors include like pumps, okay, and fans. The difference is a compressor usually compresses a gas to high pressures. And a fan also, compresses a gas, but low pressures. And a pump compresses a fluid, okay, but the fluid is, instead of gas, liquid. But they are the same device. And they are the same device. So they are analyzed the same way, okay? The best way to learn them, to go through the examples. Okay, let's say we have an air compressor. And this is the compressor here. The mass flow rate is given, 0.02 kilogram per second. Inlet conditions are given, the pressure and temperature. And exit conditions are given, exit pressure and temperature. Oh, there is also some heat loss. It is given. The question is, what is the needed power output? Okay. And how can you find it? Obviously, conservation of energy, right? Here we have some energy loss. Here we have the change in the energy of the fluid. And this should be balanced by the power input there. Okay, now what do we do here? The compressor operates steadily. That means the amount of mass within the compressor and the amount of energy is always constant. It doesn't change. Okay. So in the energy balance, this term is 0, as you see here. And we assume air is an ideal gas. Unless you have very good reason, you can always assume air to be an ideal gas. In practice, we almost always do it, except when you liquefy the air. Then you go to way down, like to -200, and then very high pressures, okay? But in general, you assume it is an ideal gas. And no mention of velocities, elevations, whatever, so we can assume kinetic and potential energy changes are 0, okay? Heat loss per unit mass is given. Okay, now the energy analysis. Okay, steady flow, so, and one inlet, one exit. Whatever energy enters must leave. So here, since kinetic potential energies are 0, the energy of the fluid is simply enthalpy, right? This is data. And entering. What is input here, energy input? We have the work consumed, the compressor consumes work, so it is input, work in. And then mass is entering, and the energy of the mass per unit mass is enthalpy. There is no kinetic potential energies. And we have heat leaving, Q out, and then mass leaving, and the mass energy of the mass per unit mass is enthalpy again. So this is what we have. The needed power input is heat transfer rate out times the enthalpy change, okay, for the entire mass flow rate. So it is this one here. So I need the enthalpies of air. If you go to air table, at temperatures of 280 Kelvin and 400 Kelvin, you can read the enthalpies, okay? And the mass flow rate is given, heat out is given per unit mass. Now I read the enthalpies, H1, H2, mass flow rate is given. So everything is available. Just plug in the values, do the calculations, and you get 2.74 kilowatt. So this is the power that must be supplied to the compressor for these operating conditions to be maintained. Any questions? Okay, no questions. So let's go to the next example. This time, turbine. Again, turbines are used a lot in practice in the energy field. And let's do some detailed analysis here. And I really ask you at home, just go through this by reading slowly and understanding everything. Okay? Because our goal is not simply to find the final result, to really understand the approach and the logic involved here. Okay, we have a turbine. This time, the work output is given. This turbine is producing 5 megawatt of power, which is a lot. And the conditions at the inlet, pressure, temperature, velocity, elevation are given like this. And at the exit, again, the pressure quality is given, which means here we have what? Saturated liquid plus vapor, right? Because quality 0.9 means 90% of the steam leaving is in vapor, 10% is in liquid. And here it is most probably superheated vapor. Okay, the velocity elevation. Questions. Compare the magnitudes of the changes in enthalpy, kinetic energy, potential energy, and determine the work done per unit mass. This is the total power. Obviously, if you divide the total power by the mass flow rate, you will get the work per unit mass in kilojoule per kilogram, right? And calculate the mass flow rate. Okay. Now, obviously, we will need the enthalpies here to do the energy analysis. So we can just go ahead and determine P1 and T1 are given, okay, at the inlet. You can just go to the steam tables and read H1, okay. And then at the exit, enthalpy is equal to, as you see here, HF plus X times HFG, okay, X2 times HFG. We know the X, which is 0.9. So at 15 kilopascal. If you read HF and HFG and plug in the values, this is what you get. So we also know enthalpy there. So what is the enthalpy change? Take the difference. As you say, enthalpy is decreasing. This is what we expect. Because you are generating, power here, that energy must come from somewhere. Because this is probably going to a generator, producing electricity and supplying it to the power lines, which comes to your house. Okay, so enthalpy change is negative. It is decreasing by 887 kilojoule per kilogram. And the change in kinetic energy, simply V2 square minus V1 square over 2. But don't forget the conversion here. It is 14.95, okay, which is kind of small compared to enthalpy change. Potential energy, G delta Z, okay, again, don't forget this conversion. It is 0.04. Now you can see that even though we have like an elevation difference of 4 meters, it is nothing compared to the change in kinetic energy and potential, the enthalpy. Therefore, this is almost always neglected. We never consider it in practice. Okay, so this is part A. Part B, now steady operation. So no change in the energy content of the device here, and one inlet, one exit. Therefore, and rate of energy in must be equal to rate of energy out as heat, work, and mass. Here, I think it is adiabatic, right? Okay, adiabatic steam turbine. So heat is 0. There is no heat transfer. And there is no work input, but there is work output. So it is on the right-hand side. And then the energy of the mass. Okay, mass flow rate times the energy of steam per unit mass, right here. Enthalpy, kinetic potential. And then mass flow rate times energy of steam at the exit, enthalpy, kinetic potential there. Okay, so this is the energy balance. And we know all of these, just calculate it. Plug those in on a unit mass basis. We get 872.48. This is work output per unit mass. We know the total. We know the per unit mass, okay? Since W power is mass flow rate times power per unit mass, okay? Mass flow rate is the ratio of the two. It becomes 5.73 kilograms per second, okay? Now, any questions here?
So I didn't get how we find output enthalpy.
Okay, let's go back here. Okay, at the exit, okay, let me do it here. We have like 15 kilopascal, right? And quality is given to be 0.9, which means right here, we have saturated vapor mixture, liquid mixture, okay? And when we have mixture, remember from chapter 3, enthalpy is HF plus X HFG. So what we do is we read HF at 15 kilopascal, and we also read HFG at 15 kilopascal. And this H is 0.9, okay? It is how you find the enthalpy. Other questions?
Thanks.
Other questions? Okay, no question. Shall we do one more or shall we leave it to the next time? Anybody?
It doesn't matter. If you want, we can continue.
Okay, let's do one more then, and then we will stop. Okay, another device, throttling valves. Okay. Now, if you look at your refrigerator, you have a throttling valve or capillary tubes to drop the pressure. Okay. Sometimes you have, devices, valves, or some kind of resistance to flow. What they do is they cause a large pressure drop. Pressure drop. So they drop the pressure. And they are usually a limited area, like it can be, let's say, a valve like this. Okay, as you see here. It may be a porous plug, or it may be a very thin tube. The cross-sectional area here is very small, so there is a lot of pressure drop because the fluid will have a hard time flowing. It is just like electric flow. If you have a thin wire, okay, and you force the electrons to flow through there, you will have a large pressure drop. I mean, large voltage drop. And here you have a large pressure drop. Then these devices are also used a lot in the refrigeration industry. Okay, and we want to know how to analyze it as a special device. And in this case, usually, okay, let's do it here. Let me see. In these devices, the heat transfer is negligible because it's a small device compared to the enthalpies involved, and there is no work involved. Okay, no work involved, and the potential energy change is almost zero. It is irrelevant, and the change in kinetic energy, it is, let's say, small and often close to zero. Okay, and this is one inlet, one exit, and m dot is constant. So what is the energy balance? Energy in is energy out. Okay, and let's do it per unit mass. Heat, there is no heat, there is no work, so there is only mass, and there is no potential. Therefore, H1 plus V1 square over 2 is equal to H2 plus V2 square over 2. Just like the nozzles and diffusers, remember? Okay, we get this. But in addition, these terms are also very small. Now this is an approximation, and in that case, what do we have? H1 is equal to H2. So H1 is equal to H2 approximately, and H is flow energy, right? So U1 P1 V1 is equal to approximately U2 plus P2 V2. That is internal energy, and flow energy is constant. Okay. Now, usually you will say, what is the big deal if it is constant? Constant, so what? We can just calculate the difference. But if, let's say, the change in flow energy is very large, okay, it makes a huge difference in other properties. So let me go through this example, and then I'll stop there. Now, let's say we have refrigerant 134, okay, and this is an actual example. It enters a capillary tube of a refrigerator as saturated liquid. So here at the inlet, we have saturated liquid, okay, which means we have like F properties at 0.8 megapascal. So the pressure is given. It is throttled to a pressure of 0.12. So here the pressure is, so the pressure drops from 0.8 to 0.12 megapascal. Okay. Determine the quality of the refrigerant, okay, the fraction of vapor mass, and also the temperature drop, delta T. Okay. Now, energy balance, throttling device. No mention of kinetic energies. Heat transfer we can neglect. Work there is none. Okay, potential, don't even mention it. So we have this classic throttling process equation, constant enthalpy. So this is a constant enthalpy process, almost, which is U1 plus P1 V1, U2 plus P2 V2. Okay. And at the end, we know the pressure. Okay. At the beginning, we also know the pressure, and we know it is saturated liquid. Okay, now, from the refrigerant table, the saturation table 12, this is for pressure, okay. If you go to 0.8 megapascal, okay, so this is a pressure, and then it gives you the temperature, and then it gives like HF, you know, whatever, HFG. This is a 0.8 megapascal. So you read these things. For saturated liquid, the F properties. You read that the temperature is 31 and the enthalpy is 95. It is a saturation temperature and HF. Now at the exit, this is the pressure given. Okay. And H2 is equal to H1. So we need two properties to determine other properties. So what is the H2 here then? It is also 95.48 kilojoules per kilogram, and the pressure is 0.12. Okay. You realize that if you go to 0.12 right here and read HF and HG, this is in between, meaning you have saturated mixture here. Mixture. So you read HF and HG, and you also read temperature saturation, which is minus 22. Okay. And you know H2, you know HF, you know HFG. You can calculate X2, the quality, which is 0.34, meaning 34% of mass is in vapor form. Okay. And what is the temperature change? Initial temperature was T1 is minus 31. Okay. And T2 final temperature, no, I mean, it is 31, so it is minus 31 minus T1. And final temperature is minus 22. So what is the difference? Minus 53.63. So approximately delta T is 54 degrees C. Okay. Now, what is the significance of this? Now, look at the fluid initially. The fluid temperature is 31, right? So above room temperature, 31 degrees. And then it passes through this valve right here. The pressure drops from 0.8 to 0.12. Nothing else. There is no other magic here, no other device. And the temperature drops to minus 22. Can you imagine that? You don't use any ice or anything. You have a fluid at what, 31 degrees, and you drop the pressure. Let's say outside maybe like, you know, 25 degrees, and the fluid temperature goes down to minus 22. Amazing, right? And this is the secret of refrigerators. This is how they operate. It is the reason that we use refrigerants there, because they have this property. Now, in case you are wondering how this device, cools the inside of the refrigerator, or let's say the freezers. Okay, like at minus, 20 degrees there, the freezers between minus 15 and minus 20. This is the entire thing. Just something, it may be some thin wire tubes or a valve like this, just something that drops the pressure. And the temperature goes down by 54 degrees in this case. Okay, so this is the heart of a refrigerator or freezer. Now you can ask, where did that energy go, right? If temperature is dropping this much, then the internal energy must be dropping, right? So something must be increasing. If internal energy, U, goes down, then something must go up by the same amount. Okay. Obviously, then P1, V1 will have to go up drastically. And if you look at the numbers here, at the inlet, P1, V1 flow energy is 0.68. At the exit, P2, V2 is 6.68. That is 6 kilojoules increase. And U1, initially 94.8, and at the end, 88.8. So it is dropping by 6. Therefore, the decrease in internal energy is equal to the increase in flow energy, PV. Okay, let's put a minus here, because as one increases, the other one decreases. And all the values here are, they are exactly the real properties of refrigerant 134A there. So this is the story of a refrigerator, how it operates. Any questions on this?
I think no.
Okay.
It's completely clear.
Okay. So you will also read this at home. Okay, so I'll stop here. Okay, next time we will continue from where we left off. And then Mehmetcan and you will decide the proper time. Okay. And then we will have the lecture next week at that time. So you all have a good evening, and I wish you well at the exam next week, or physics or other exams, whatever you have. And I ask that you read the entire chapter before you come to class next time. All right.